All right, we're ready to go. So today we're gonna, as you can see on this slide, we're gonna do exam from 2016. I'll just go over all of the questions, not necessarily doing all the calculations in full detail because you actually have the solution file. I've put it on the website. But the important thing is I'm going to go through the reasoning and what you should think of when solving these questions. And also I will talk about Blackboard tests and how, since obviously Blackboard tests work quite differently than usual exams, I'll say a few things about how these questions may be translated in the Blackboard test and what you will actually be facing on the day of the exam. And all right, so let's just go. This exam from 2016, it's pretty good. So it's a lot of questions which, it works on the things you're supposed to have learned. There are no surprises. So if you can do this and really understand everything which is going on, then that's great and you're basically good to go. So let's start. First exercise is about a renewal process. So we say that there's a renewal when, so we're tossing a coin repeatedly. So it's a bias coin, probability P of being heads. And we say that there's a renewal when there's two heads consecutively. Specifically, so renewal happens at the second head. So whenever a run of two consecutive heads is completed. And so we have the usual questions on this thing. So first question, let UN be the probability that if there's a renewal at time t, then there's a renewal at time t plus n. So find the value of UN, and then it asks to show the generating function has this form here. So, well, that's nothing very special, I guess, but let me write things down. So I hope things are still readable here. Yeah, should be okay. So if there's a renewal at time t, it means that we've had two heads in a row. So there was a head at t minus 1, there was a head at time t. So u1 equals p, I guess. So exercise 1. Question A, U1 equals P because there was a head at time T. So we only need to guarantee one more head. So we just need head, I guess heads, at time t plus 1, which has probability p. And then un for n bigger than 2, well, we're gonna get p squared because that's the probability of getting two heads in a row. And that's just because probability of getting a head at t plus n minus 1 and t plus n, since this is independent of what happened at t minus 1, probability of getting, probability of getting two heads in a row, so at t plus n minus 1 and t plus n, independently of anything at time t or earlier. So what I'm writing doesn't really matter, and you can see on the solution file. The point is it's p squared because it's a probability of getting two heads in a row, and the thing we're conditioning on doesn't matter because it's too far in the past. And then show that the series has this form. Well, you just go ahead and do it. U of s is sum for n equals 1 to infinity of un s to the power n. And we've said, so u0 is equal to 1. That's u0. u1 is equal to p. And then we have, after that, they're all p squared. So it's p squared, sum for n equals 2 to infinity of s to the power n. And that thing, that's a geometric series. And you will know that a geometric series, so we'll get the first term is s squared divided by 1 minus s. Geometric. So here's a reminder that, you know, the answer, this answer, u of s is, where's my file here? The answer u of s is 1 plus ps plus p squared s squared over 1 minus s is given. So you can use that to find the thing. So if you were having troubles with finding un equals p squared, what you should do is think, well, what value of un could give me this? And you should think, well, the traditional thing is to decompose this 1 divided by 1 minus s into the geometric series. And then you would see that there's p squared times s to the power n for n bigger than 2. And then you notice, of course, that this has to be u1. And this is u0. I went fast for u0. u0 is 1 because if there's a renewal at time t, then there's a renewal at time t with probability 1, of course. If so on a Blackboard exam, we can't test your reasoning, really. So instead, what would be happening is either, so you may get, for example, the question could be, u of s has the form a plus bs plus, say, cs plus ds squared divided by e plus fs. And you'll be asked to enter the values of a, b, c, d, e, f. That's one thing which could happen. Another thing which could happen is we would tell you to work out u of s on your own, and we would check it by asking for, say, u of 1/2. And then you would have to enter u of 1/2 as a fraction. So we'd say u of 1/2 is a divided by b, and then you'd enter the integers a and b. That's basically how we would test finding it. There could also be a multiple choice. So I'd give you various things which look like that. Only one of them is correct, and you'd have to choose the correct one. All right. Question 2. So now Vn is a probability that there's a renewal at time n, and we don't care about conditionally on having a renewal before. And then again, we're asked to find v of s. So you'll notice that v of s is like u of s, but it's been stripped of the first two terms. And that's basically enough for us to guess that Vn is 0 for v0 and v1. And then there are p squared, and the p squared is actually given again. So still, that's a guess from the question. So we need to actually say why. So v0, so that's question B. v0 equals 0, and that's also v1. Because so by definition, in a delayed renewal process, you don't start with the renewal. So that's more of a convention. for delayed renewal process. And maybe check the answer file, maybe they explain that differently. And V1 equals 0. Well, you can't throw 2 heads if you've only thrown 1 coin. Need to throw 2 coins before a renewal. And of course, Vn equals p squared for n bigger than 2. Explain why Vn equals p squared. So it's just the probability that you throw two heads in a row. Probability of having heads twice in a row. So from this p squared, the same calculation I just did gives us the value v of s equals p squared s squared divided by 1 minus s. At that point, there's no difference. Next, let Fn be the probability that given there's a renewal at time t, the next one is at time t plus n. So, and actually the question is just, what is the value of f2? So this one, you just need to think about it a little bit. So you have 2 heads in a row at t minus 1 and t. And what's the probability that there's a renewal at t plus 2? So we're asking something like so here I have t minus 1, t plus 1, t plus 2. So we know we have heads here and here. And we want, what's the probability of the next renewal being here? So for the next renewal to be here, we want an h and also an h here. Because then we have 2 in a row, so that makes a renewal. Problem. Now we have a renewal at t plus 1. Because we have h and h. So actually we can't have a renewal at t plus 2. So interestingly enough, f2 equals 0. Well, we can have, yeah, so we can have a renewal at t plus 2 like this, but then it's not the next one. And this is why f2 equals 0. Okay, and then final question for the renewal process exercise. Using that v is u times b, so if you remember, so v and u, well, we just said what they are. It's v is probability of a renewal happening, u is probability of a renewal happening after a renewal, so it's like the not delayed version, and b is the first renewal, the one which is different, which is the delay. And find the expected number of tosses until the first renewal. So that you should know from the lectures that what we're looking for is b prime of 1. So this question is in disguise, what is b prime of 1? And so you have to do it. And to do that, so you write b of s is, so v divided by u, was it u? Yeah, v divided by u. So it's p squared s squared divided by 1 plus ps 1 minus s plus p squared s squared. So I did a few things. Well, basically I put this 1 minus s down here. And I'm not going to do any more. You know what to do. B prime of s equals, it's pretty messy. It's pretty messy, but you can find b prime of s. It's a fraction. So this squared will be at the bottom. Then you get this prime minus this. that this prime times this minus this prime times this, and so on. B prime of 1 equals, so it's some work, but I'll tell you the answer is 1 divided by p squared plus 1 minus p, which is pretty curious, but that's fine. So if p was half, we'd get 3/4. Ha. Okay, so this is the exercise on renewal processes. It uses a bit of everything. There's, there's U's, there's V's, there's F's, and there's B's. There's not much F. As you could see, question C was, you do see my cursor, I think. Question C was pretty short. And I guess, if that could have been a question, what is Fn? Then you should use the formula which relates the function, the generating function f and generating function u. Though maybe it's too messy and it's not actually doable. But there may be questions like, what is Fn? Okay, next exercise. Now we have a Markov chain. Find the communicating classes and which states are transient and which states are recurrent, the usual stuff. So, for Markov chains, the things which you need to know how to do is, find the classes, find stationary distributions, compute the expected times until entering until being absorbed, or the probability of reaching a certain absorbing class. What did I miss? Find the periods and apply the limit theorems when it's aperiodic. These things. Here, so always a good idea to represent your Markov chain by a graph, because it's more visible this way. So for this one, so I have 1, 2, 3, 4. Pretty small, really. 1, 2, 3, 4. So 1 can go to any of the others with probability 1/3. 2 loops back onto 2, so that's pretty interesting. And 3 and 4, they stay together. So 3 goes to 4 with probability 1/4, and 3 loops back with probability 3/4, and then 4 is half and half. Okay, so the classes, remember the classes are two vertices, 2 states are in the same class if I can go from one to the other. So here, you can't go back to 1 from anywhere, so 1 is its own class and it's open. Is this asked in the question? Well, it's an open class, but 1 is transient because we can't come back. It's the same thing. 2 is its own class because I can't go anywhere from 2. I can only stay here. So 2 is its own class and it's recurrent. And then 3 and 4, well, they're together because I can go from 3 to 4 and from 4 to 3. They form a closed class, which is recurrent. Well, closed class with recurrent states. Okay, find all the stationary distributions. So, you know what to do. So, you're going to have 4 values, pi1, pi2, pi3, pi4, which add up to 1. And we're going to solve the equation for stationarity. So given that 1 is transient like this, we can't come back. You know already that pi1 will be equal to 0. But still, let's check that it happens. Well, write your equations. So remember, the equations are, if I start with distribution pi, I still have distribution pi on the next step. So for example, the probability of being at pi1 in the next step, I wrote it wrong, sorry, I wrote this wrong. I'm looking at the matrix. There's none of this arrow, and there's that arrow. So it doesn't actually change results at all, but let's be correct. So pi1 is 1/3 of pi1, because to be at pi1 at the next step, you had to be at 1 at the next step, you had to first be at 1, probability pi1, and then stay probability 1/3. Similarly, pi2 is 1/3 of pi1. Either I was at 1 and moved to 2, or I was at 2 and then I was stuck. Then pi3 is going to be 3/4 of pi3 plus 1/2 of pi4, and then pi4 is going to be 1/4, well, 1/3 of pi1 plus 1/4 of pi3 plus 1/2 of pi4. And so when you solve this, you will get pi1 equals 0, of course. Then pi2, there's basically no restriction on pi2. So you can see this equation just becomes pi2 equals pi2. Are you still seeing what I'm writing? Barely. And then for the other ones, well, you're going to have to solve this. And of course, as things happen, they're equivalent. And we get pi4 equals 3/2 of pi3. And now, so if you've practiced a little bit, so you can see that given that there's two irreducible classes, basically there's going to be a parameter for your solutions saying how much weight we give to the class containing 2, how much weight we give to the class containing 3 and 4. And as you can see, pi2 is basically free. So one way of writing the solutions, you can parameterize them by pi2, 0, say pi2 is alpha, and then pi3 and pi4, there'll be 1 minus alpha times, so I guess it's 2/5 and 3/5, yeah, 2/5 and 3/5. So because everything has to add up to 1, and this one has to be 3/2 of that one. We could also find 3/5 and the 2/5. Maybe if I was too fast, but you can do it the way you like. But if you were looking only at the irreducible distribution for 3 and 4, well, one on the right is 3/2 of the one on the left, and they have to add up to 1, so 3 plus 2 equals 5, so 3/5, 2/5. And then add the 1 minus alpha to fit with the alpha here. Okay, and so with alpha, of course, has to be between 0 and 1. The next question, something we haven't done together. So good practice. Maybe that was in the earlier classes. Prove by induction formulas for the distribution, well, for the probability of being 1, for the probability of being 2. So this is just, so it's good that the answer is given, because you can use induction the way you like. Well, as in, you don't have to guess things to do the induction, just do it. So initial step, I don't know how you usually write this, initial step of an induction. So n equals 0. So p of yn equals 1. Well, p of y0 equals 1. So as it's given on the sheet, we're starting at state 1. So that's 1, and that's 1/3 to the power 0, so we're fine. P of y0 equals 2. That's 0. And yes, 0 is indeed equal to 1/2 times 1 minus 1/3 to the n, well, to the 0, because this is 1 and we get 0. And then induction step. So assume it's true at time n. and show that it holds at time n plus 1. So assume that p of yn equals 1 and p of yn equals 2 are given by the wanted formula. So given as in the text. Then p of yn plus 1 equals 1. So use your Markov chain. To be at state 1 after one extra step, we had to first be at step 1 before and then take the step where we don't move. So it's equal to p of yn equals 1 times 1/3. 1/3 being the top left coefficient of the matrix. And of course, that's indeed 1/3 to the power n plus 1. Meanwhile, p of yn plus 1 equals 2. So to be at state 2, either we were at state 2 before, or we were at state 1 before, and then took a step to go to state 2. So we get p of yn equals 1 times 1/3. So this 1/3 is the first line, second column term of the matrix, plus p of yn equals 2. So now you have to mess around with your formulas, but we get 1/3 to the n plus 1 plus half of 1 minus 1/3 to the n. And it should give us exactly what we want. It doesn't look like it will, but it should. Let me think for a second. So yeah, so we get 1/3 minus 1 to the power 3 to the n times 1 minus there's a 1/2. You got to write it properly, but it's going to work out. So how do I want to write it? I know. So 1/2, let's do it like this, minus 1 divided by 2, 3 to the n, plus 1 divided by 3, 3 to the n. And so we get 1/2 minus, so 1/3 minus 1/2, that's minus 1/6, 6, 3 to the n, and that's 1/2 minus 1/2, well, 1 divided by 2, 3 to the power n plus 1. I mean, play with your fractions the way you like, and so we get 1/2 times 1 minus 1 divided by 3 to the power n plus 1. And there we go. So the rule, now what you have to do is use your induction step and then take a step of the Markov chain. Okay, and now final question of this exercise. Assuming that the distribution of yn converges to a stationary distribution of the chain, so it converges to one of those things with alphas, which one will it be? Well, if we look at our formula, the limit is 1/2. So if it's one of those, it has to be the one with alpha equals 1/2. And that's your answer. D is alpha equals 1/2 by taking the limit in p of yn equals 2. And it makes sense that it's 1/2, because if you look back at this diagram, so at every step you have probability 1/3 of going into this block and 1/3 of going into that block. and 1/3 of delaying the choice. But the probability of going towards 2 or towards 3 or 4, they're the same. At any point, probability of landing into this block or that block is the same. And so this means that we want the two blocks to have the same mass total. And we said that, you know, alpha was the mass given to this one, and 1 minus alpha the mass given to that one. So alpha equals 1, 2 is the only one which gives us 1, 2. 1/2 is the only one which gives us the balance between the two blocks. So it has to be this. Okay, so that's exercise 2. Now let's move on to exercise 3. So there's a lot of Markov chain exercises in this one. So let Xn be a Markov chain which looks like that. And so first thing to do is draw it. So let's do that. New paper. So P, as you can see, it's actually a cycle. So what's going on is I have 1, 2, 3, 4, 5. And we're basically going this way with probability P, and we're going the other way with probability 1 minus P. So 1 can go to 2, probability P, or back to 5, probability 1 minus P, and so on. So show that the chain is irreducible and aperiodic. So it's irreducible because I can go from anyone to anyone. I can go from 1 to 3 in 2 steps, from 3 to back to 1 in 2 steps, and so on. You can make a full cycle. The simplest thing you can do is say, I can make a full cycle 1, 2, 3, 4, 5, 1 in 6 steps, and so I can go from anyone to anyone. It's aperiodic. So why is that? Remember, so that the period is the same for each state, and the period is the GCD or the HCF of the time it can take to return to your starting point. So to return to 1, I can either go to 2 and go back, that's 2 steps, or I can make a full cycle, that's 1, 2, 3, 4, 5 steps. I said 6 at some point, 5 steps. And the GCD of 2 and 5 is 1, and that's why the period is 1. I'm going to sneeze. Sorry. And that's why we have irreducible and aperiodic. Verify that 1/5 everywhere is a stationary distribution. So it makes sense because that it's this one, because you know there's a lot of symmetry going around. All the states have basically the same role, so they should have the same value. In any case, if you write the equations, if you write the stationarity equations, they will all reduce to 1/5 equals P times 1/5 plus 1 minus P times 1/5. And that's obviously true. So 1/5 everywhere is stationary. Hence, the next question, hence prove that probability of being I converges to 1/5. So that's theorem from the course. So finite number of states, irreducible, aperiodic, all of these things together imply that we converge to the stationary distribution, and the stationary distribution is unique in this case. So when you combine all of that, probability of xn equals y converges to 1/5. So be sure to state everything which needs to be stated. So finite state, because that implies positive recurrent, uniqueness of the stationary distribution, aperiodicity, and then we're good. Next question. Assume that P equals 1. Is the chain still irreducible? So if P equals 1, basically we don't have this anymore. We only go this way. So it's not exactly a Markov chain anymore because it's not random. We're deterministic, but that's fine. Is the chain still irreducible? yes, I can still make this cycle. So I can go from anyone to anyone. Is the chain still aperiodic? No, because now if I start at 1 and want to return to 1, the only way I can do this is by doing this cycle. It'll take 5 steps. And the only way of going back to 1 in any way is by just taking multiple instances of this cycle. So I can go back in 5, 10, 15, 20 steps, but nothing which is not a multiple of 5. And so the period is actually 5. And I think that's all for this exercise. Yep, now exercise 4. A gambler repeatedly plays a game where he wins £2 with probability 1/3 and loses £1 with probability 2/3. Has an initial fortune of £1 and he stops playing when he reaches 0 or £4. So it's a kind of gambler's ruin model. So give transition matrix of this thing. It's we can model this again with a little graph. It could help. So we have 0, 1, 2, 3, 4. So we jump up by 2. Interestingly enough. So we jump by 2 with probability 1/3 we said. Yep. And we go down by 1 with probability 2/3. Oh, that's it's kind of nice Markov chain. However, when we've reached 0, we stay there, and when we reach 4, we stay there, and we say that we jump from 3 to 4 because that's the satisfied point. So the graph is a bit messy, very messy, but that's fine. You get what's going on. So give the transition matrix. So 0 is a state, so let's be careful, but there's 5 lines, 5 columns, 5 rows, 5 columns. So the transition matrix, so there'd be 1 here, 1 here, and zeros. So 1 can go to 0, probability 2/3, can't stay at 1, can't go from 1 to 2, can go from 1 to 3. 2 goes to 1 with probability 2/3, doesn't go to 0, doesn't go to 3, doesn't go to 2, doesn't go to 3, goes to 4, probability 1/3, and 3 can go back to 2, probability 2/3, doesn't stay put, and can jump to 4, 4/win. Okay, so find the probability that the gambler runs out of money. So that is one of those probabilities of absorption questions. So let's say Pi equals probability of running out of money starting at I. And the question is, find P1. So we have the boundary conditions, P0 equals 1, P4 equals 0, and then we just need to write our equations. So P1, which is the one we want, it's 2/3 P0 plus 1/3 P3. P2 is 2/3 P1 plus 1/3 P4. So P4 is 1, remember. And P3 is 2/3 P2 plus 1/3 P4. So you can solve this. Shouldn't be too bad. And I'm not going to do it. And the result is P1 equals 18/23. And the other question is, find the expected number of games before you stop playing. That was B. C. So we're going to call EI equals expected number of games. And it's the same thing. E0 equals 0. E4 equals 0 this time. There's both zeros because this is when we stop playing. Let me check. I should have read. I guess I should have read the exercise more carefully, right? Because it says the state space actually includes 5. It won't change our results, but okay, fine. So there's also a state 5 here, and 3 jumps to 5 actually. So there's an extra column here, 1/3 here, and 1 here. These are 0. This is the version where 4 and 5 are 2 separate states. In which case you get the P5 here and P5 equals 0. But this is modeling the thing as asked by the question. E5 equals 0, we can go back to this. And so E1 equals, so either probability 2/3 is, well, okay, let's do it the way we usually do. You have to play one game, and then probability 2/3 you reach 0, so you kind of stop, and with probability 1/3 you reach 3, and you move on. E2 is you have to play one game, and then 2/3 of E1 plus 1/3 of E4, so you'd stop. E3 is you have to play at least once, 2/3 of E2 plus 1/3 of E5. And you'd solve this. It's not hard. And the answer is E1 equals 42 divided by 23. Okay, and that's all for Markov chains. So now let me talk a little bit about how these would work on a Blackboard test. So let's go back to 2. So find the communicating classes. So what probably could happen is you'd be asked, it would be a multiple answer question. So there would be like, please tell me what states are in the same class as state 1. And so I'd give a whole list, and you have to pick and choose which ones are correct. And there would also be the option, of course, it's actually alone. So there'd be one option, 1 is alone in its class, and then you may be able to select any state you like, which could be in the class. And there'd be questions like, is the class containing 3 transient? Which is the class containing 3 open, closed, and these things. Find all the stationary distributions. So it wouldn't come out in this form, but probably you'd be asked to enter a fraction. And that could be a question like, there's a stationary distribution for which pi2 is given by half. And I'd ask you, please tell me what pi4 is. And we had this formula with pi2 is alpha, and pi4 is 3/2 times 1 minus alpha, 3/5 times 1 minus alpha. So you just have to fill in the fraction. That's one way of doing it. Prove by induction. Probably this one would be as a multiple choice. So you wouldn't have to do the induction, lucky you. And question C2, well, it's kind of the same thing as I said with question B. I could also be asking you what the limit of P of Yn equals something R. And then you have to give me the appropriate invariant distribution. For 3, so there could be a question, what is the period? And you'd have to fill in an integer. Again, I can't ask for your reasoning, so I'd ask for the result. That's the best we can do. There would be, well, what it is something, a stationary distribution. That could be 1. Then you have to fill in yes or no. And for the limits, well, same thing as before. And again, p equals 1. So you could be asked this or that with a yes or no, or what is the period, but there would be no explain your answer type questions. For exercise 4, so you'd have to fill in a fraction for these. They would be the most likely. And so, as I said before, when asked to fill in a fraction, that means give 2 integers, a and b. Okay, let's just finish with the Poisson process. So exercise 5. Let's put this in big again. Assume that emails arrive in an account as a Poisson process with rate 4 per hour. What is the distribution of the number of emails between 9 and 11 a.m.? So you know how Poisson process works. So it's going to be Poisson with parameter 4 times the length of the interval. So 5a Poisson parameter 8. 4 per hour, 2 hours. We get 8. Next, what's the probability that no emails arrive between 9 and 10 a.m.? So between 9 and 10 a.m. we get the Poisson parameter 4 variable. So the probability that the Poisson parameter 4 is equal to 0. So that's e to the minus 4. No surprise. So in the Blackboard test, you can't enter e to the minus 4, so maybe you'd be asked a decimal representation. So I tell you, write it as a decimal, and I tell you precision of two digits after the decimal, something like that. But this one is actually 0.0183, so I ask for 2 significant digits or 3 digits after the decimal point, something like that. And another option would be multiple choice with e to the minus different things, or I'd say it's e to the minus a. What is a? Assuming that it's an integer, then you can just fill out 4. Okay, next, given that there are 6 in 2 hours, sorry, I'm reading the wrong file. Given that there's 6 emails between 9 and 11, what's the probability that exactly one of them arrives before 10? So remember, these 6 emails, they're distributed as uniforms on the interval 9-11. Oh, 9-11, great. Because that's one of the theorems we've done. So basically, the number which arrived before 10 a.m. is a binomial with 6 trials, and each has probability half of happening. The half because before 10, that's an interval with length 1, which is half of length 2. So it says the probability that binomial with parameter 6, 1/2 equals 0. So I'm using this notation. This is not fantastic notation because this is not the variable, it's a distribution. But it's good shorthand. But this is shorthand. So in a written exam, which is not what you'd have, you would have to write the number of emails arriving before 10 a.m. is a binomial with parameters 6 and 12. So the probability that it's not 0, it's 1, is given by So let's see if we know what we do. 6 times 1/2 to the power 1 times 1/2 to the power 5. So of course it's just 1/2 to the power 6. And so 2 to the power 6 is 128. No, 64. 6 divided by 64. 3 divided by 32. In a Blackboard test, we'd ask for the reduced version of a fraction. So be sure to reduce your fractions. Next is D. So show that the distribution function of S2, which is the time until the second email arrives, is given by this formula. So distribution function, so that the cumulative distribution function, sometimes we say, or probability distribution function, which doesn't help, but P of S2 smaller than T. So that's a probability that we've had at least 2 arrivals before time T. So that's the same thing as P of N0T bigger than 2. And we can just write this. And of course, with the Poisson variable, the best we can do is by saying it's 1 minus P that N0T smaller than 1. And so we get 1 minus e to the minus, so it's 4t, minus e to the minus 4t times 4t divided by 1. So that's factorial 1 here if you like, and factorial 0 here. They don't really matter. And so we get 1 minus e to the minus 4t times 1 plus 4t. Okay. And final question. Each email is marked as spam with probability 3/4 independently of other emails. Describe the process of arrivals of a non-spam emails and give a reason for your answer. So this is just the theorem from the course. It's literally the marking theorem. So each occurrence of your Poisson process is kept with probability 1/4. And so the result is a new Poisson process with rate 1/4 of the original. So the new process is a Poisson process with rate 1. And you just have to say, from the course, it's the marking theorem. Okay, and we're done with the exam. Of course, I didn't write everything in detail, which is why we did it pretty fast. But let me again comment about Blackboard. So we did A and we did A. So B, we did A, we did B. And I said, yeah, it could come, you could be asked to write it as a decimal or to fill in whatever's in the power of the exponential. For C, so it would be asked probably as a decimal since it's a fraction. That's good. For D, the most likely thing, so either there'd be a multiple choice, or we'd give you numbers. I'd replace these by A, B, C, and D, and you'd be asked to tell me what A, B, C, and D are. That would work fine. And for the last one, well, best we could do is ask for the parameter, for the new parameter of the Poisson process. And yeah, that's it. So other things I want to mention about Blackboard. So in Blackboard, the questions will be randomized. So not everyone will have the same sets of questions. You may have a slightly different renewal process, slightly different Markov chain, or you may be asked to give the station distribution at a different point, and so on. So be careful about that. Of course, the point of this is to prevent cooperation. Though we can't prevent it completely, at least this should convince you that you should work on your own tests. Things will be randomized, and yeah, I've told you what kinds of question you can expect. That's about it, really. So feel free to ask me any more questions. So I prefer the Blackboard message boards, but you can still send me emails. Yeah, I think that's it. So I'll see you if you have any questions. Otherwise, good luck for the exam. Goodbye.